Mr. Brown, you're muted.
There we go. Cool. Not sure how that happened. So yeah, y'all didn't hear anything I said, did you? So let me just. Sorry, guys in class, we can just hear myself say all that over again. So let me try that again. We'll start with the important part. I love doing this. Okay, so again, we have two types of averages in calculus. We have the average rate of change and then the average value. One of those is new, one of those is not new. I teach them though both in the same day because I do want to make sure we can kind of hammer home the differences between the two averages. They are calculated differently, we do find them differently. The first one that I want to talk about is the average rate of change, which if this was like not a calculus class, an easy example that you could be looking at with the average rate of change is you drove 300 miles in 6 hours and then calculating your average velocity. Hold on, why is my screen not sharing again? Cool. Hey guys at home, can you see your screen now? I don't know why it unshared.
Yes, sir.
Cool. Okay. So when we're trying to find that average velocity, we have that 300 miles divided by the 6 hours, which gives us that 50 miles per hour. I do that not because like this is how a question is going to be worded in this class or on the AP exam, but I think it's good to remember that like these new things we're learning is just connecting to stuff that we have already done. Like when we say average rate of change, like it is representing a rate in many ways. So to kind of connect this to calculus, and again, many of you had me definitely first semester probably recognize the slide in some ways. And that's going to be the definition that we use for the average rate of change. So first new formula, and again, it's not going to be really new. When we see average rate of change, I just want you to think of this as just your slope. Like it is just slope. Nothing new, you've been doing it since the 6th grade. But average rate of change for us, so we have the change in y over the change in x. Why am I reteaching this? You're like, Mr. Brown, we know what slope is. I'm doing this because I often find when people are asked to find the average rate of change, and they're sitting in a calculus class, they want to like so badly like find a derivative or something like that. But again, we're not going to kind of make it more complicated than it is. Average rate of change is just your slope, the change in y over the change in x. No derivatives involved. Did also want to review graphically what that represents. The average rate of change is basically the slope of a secant line. So slope of a secant line, which you might remember from first semester. A secant line is when you're connecting 2 points on the graph. So starting when x is -2, ending when x is 3, average rate of change would help you find the slope of that line. Why will we look at this in the context of this problem? Maybe you're given a table instead of a graph. So instead of finding the derivative, the only possible thing you can do is maybe approximate it using an average rate of change, or kind of approximate it using a slope. We'll get into the word problems towards the end of class. I just want to kind of give you that basic formula for now. But again, big mistake I often see, people want to use a derivative, but just remember average rate of change is just the slope. So as an example, and again, it literally is this easy. To be honest, I have seen questions on the AP exam where it's like a multiple choice question. It says, hey, find the average rate of change. Don't make it more difficult than it is. Average rate of change is just the fancy way of saying slope. Don't find a derivative, just find the slope. So if I'm looking for the average rate of change, it is the change in y over the change in x. 4 cubed is what, 64? 64 minus 1 is 63 over 3. So that is the average rate of change. And again, at the second half of class, we'll kind of connect this to like some situations. Like how does this relate to PVA or any of those other like input-output problems that we looked at. So then the other type of average that we have in calculus is not the average rate of change, but it is called the average value. And this one, like we have seen it in some contexts, but it is mainly going to be new. So the average value literally is going to be connected to your good old average you used in elementary school. So try to find like the most elementary school problem I could. Anne has 3 cookies, Bill has 5 cookies, Charlie and Dan have 6 cookies each. What is the average number of cookies we have? Again, you're like, Mr. Roundhouse is calculus, like we'll get there. But how do we find the average? You add up the total number of things. So we would have 3 plus 5 plus 6 plus 6, and then divide it by the total number of things you have. And there's a total number of 4 people. We know how to find average. You've been doing it forever. How does this connect to calculus? And why I show you this is so you can kind of remember where the formula comes from. When in calculus have we had to find a sum of a bunch of things? Riemann sums. That is not spelled like that, i.e. So that is a Riemann sum. So in some ways, when you're finding an average, you're kind of finding a Riemann sum. What do we use a Riemann sum to basically approximate? The area. In calculus, what is the area represented by? An integral, specifically a definite integral. So it doesn't look like it, and your 4th grade teacher definitely didn't describe it this way, but basically when you're finding the average, that top part of the average was basically a Riemann sum approximating a definite integral of some function. What function would this be? This will be like a function of like the number of cookies, I don't know, like C of x. So that's where the average value formula comes from. So this is really the new formula you definitely want to memorize for this topic. I'll give you the formula first. So this is going to be the average value of f of x on the interval from a to b. So again, average value is going to be different from average rate of change. Average value is going to be literally what is the average of f of x. So you're going to add up all your f of x. How do we add up f of x? We're going to use an integral. That's going to be the integral from a to b of f of x dx. And then we want to divide it by the number of f of x's you have. Well, how many f of x's you have? You have the same number as x's you have, which start at b and end at a. So that is the average value formula. On the AP exam, to be honest, and I often write this way as well because it's a little less complicated, instead of putting everything over b minus a, it will be written in front as a coefficient. But you should be able to recognize that those two expressions mean the same thing. And then I did want to emphasize this is called the average value of f of x, and that is what is being plugged into the function. Whatever function you are integrating is the one you're finding the average of. And that is going to be a big idea with this. That's going to be very useful when we're doing these word problems. So what you're integrating, this is the function you're finding the average of. What do I mean by that? Say you know the velocity function. If you wanted to find the average velocity, you technically could just integrate the velocity function from a to b divided from b minus a. Or maybe you connect it to, let's see, that first problem we did with homework 2. On that day, we had like the oil leaking into the lake. So if I wanted to find like the average rate that oil was leaking at, I could integrate the function that was being represented by the oil leaking. Thinking of your quiz yesterday, we had a function representing people getting in line for a drive-through to get a vaccine. If I wanted to find that average rate that people were getting in line, I could plug in that function for where the f of x is. So whatever function you're integrating in this formula is what you are literally finding the average of. So that's kind of how that comes into the context of the word problem. I do want to talk about the graphical meaning as well. I don't think it's as important for average value. I think it's more just kind of like neat and interesting. And I guess I am the calculus teacher, so I think it's neat and interesting, but what does it represent? The average value from 2 to 3 is literally, if you could physically add up every single y coordinate starting at -2 and ending at 3. And again, you physically can't do that because this is a continuous function. So you have like -2, -1.9, -1.99, -1.998. Like you have an infinite number of decimals, so you can't really add up all the y values. But if you were able to add up all those y values, then what the average value is representing is literally the average of all those y values, which visually is going to happen somewhere for this one, like in the middle of the function. So maybe that blue line does represent the average of the y values. And what makes that interesting and kind of how we can connect that to an integral is I outlined that function from 2 to 3. We know that that function has an area represented by an integral. It's an irregular shape, like it's just some shape, but this integral can give you the area of it. The average value basically tells you like, hey, whatever that average value is, if you drew a horizontal line there, it would form a rectangle. And what's kind of unique about that is this rectangle would have the same area as that irregular shape defined by the function. So it's kind of like, hey, let's just pretend all the y values are the same, and that is kind of visually where the average value shows up at. Again, I do think the graphical meaning is not as important, but it's just kind of like interesting to see, and we'll kind of see how that works in the example on the next slide. But if at a minimum, definitely do need to make sure you know that formula written in either format. So go ahead and try this one for me. Sometimes these problems are on the calculator section, or it could be on the no calculator section, so you do want to make sure you can do it both ways. For the sake of time, go ahead and try this one with a calculator. You could do this one without a calculator, but go ahead and like set it up. I want you to find the average value of f(x). So show your setup, use your calculator to find it, and then we'll talk about how that is connected to what you see in that graph. But again, sometimes these problems are going to be calculator problems. Sometimes they will be no calculator. And as usual, just make sure you're exact to 3 decimals. You can't type this all in at once. I'm going to kind of type in the integral separately, but you can definitely do it all at once. And so that integral, again, you very well could have done that integral by hand. Like the antiderivative of x is 1/2 x squared. You can definitely do the integral of 2 cosine of x. In the calculator, you get 3.770 around to 3 places. Divide by b minus a. Well, b minus a would just be 3 pi over 4. 1 over that is going to become 4 over 3 pi. I'm just going to kind of multiply that by 4 divided by 3 pi in parentheses. And we get, and what you should get, is the average value is 1.600. If you round to 3 places, that last number is 2. But basically, 1.6. Yes?
You know, different answers.
Mine was 4.190.
Yeah, that's what.
Cool, it is wrong because I can't type it in. I typed in 1 plus 2 cosine of x. Let me try that again. Da 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 da. So yeah, definitely if you're using calculator, don't be me and type it in wrong. That is x plus 2 cosine of x. I typed in 1 plus 2 cosine of x. And that integral, does this look better, 4.190?
Yes.
Yes, okay. So then multiply that by 4 divided by 3 pi. And we get 1.778. That look better? So that is the average value. And again, sometimes the question would just be like, hey, what's the average value? And then that's your answer, and then you would stop there. Again, the visual is not as important, but I do think it's kind of neat to see. So this is the graph of that region. So if we're going from 0 to 3 pi, there's all those y values. If you could physically add up all those y values, their average would be about 1.778, which is somewhere like right here. So then the unique part about that, if you drew a horizontal line at that average value, it would form a rectangle. And the area of that rectangle is the exact same as the area of that purple region. So that's kind of what the average value is doing. Main thing we're going to be focusing on today, though, is just like how do we find the average value. So like setting it up, typing into your calculator correctly, or find the antiderivative by hand, and then getting the answer. That's the first part of these notes, kind of looking at those two formulas, average rate of change and then average value. The second part of notes, we're not going to do all of this today. There's not enough time. But I did want to go ahead and look at this worksheet I shared with you in OneNote. So this worksheet does have average rate of change on it, and it does have average value on it. It also has a lot of old stuff on it from the first half of the unit that I do want us to kind of look at and review. My goal, and we'll see kind of how the time works out, I want to get at least this first page done today. If we don't do all of them, no big deal, we'll just save it for tomorrow. I will say, disclaimer, most of the new stuff is going to be on the second page. The second page does mostly have the average value and average rate of change. So this first page, while it doesn't connect directly to what we're doing, it's good to review, especially looking at some of the quizzes from yesterday. Always kind of good to review. So what I've done and how this kind of sets up, I'll do the first row for you and then give you a chance to try some of these other rows yourself. So I chose the PVA one. I think most students have like a better just like gut understanding of like the position, velocity, acceleration. I give you a graph, not a graph, but a table of V of t. I give you an initial condition, the initial position, which is at 5 meters. And I basically wrote this table with like the first columns an expression. Some of them are like integrals, some of them are just like a value, some of them looks like a rate of change. And I want us to be able to do two things with that. I want us to first be able to just find that number if we can, and then interpret it in context. And I have found that like there's some students who are like really, really good at finding the numbers and not so good with like explaining it well. And then some people are like, well, I can describe it all day long. I just don't know how to get to the actual number. And then hopefully you're not bad at both, or maybe you're good at both. But let's go ahead and look at that. I did add one thing. If we have to use a Riemann sum, also just for review, we're going to use a trapezoidal sum with two subintervals. We haven't done one of those in a while. Doesn't hurt to review. So this first row, I want us to find just the integral from 1 to 7 of v of t. So let's think to ourselves, how would we find the integral from 1 to 7 of v of t when provided with that table of v of t? And so your options are, maybe this is like a first FTC problem, or maybe you just read from the table directly and get an answer, or maybe it's a Riemann sum. So if we want to find that integral, what kind of method would we use to kind of evaluate that integral? This would be a Riemann sum. So this one is, I chose a trapezoidal one. Probably been a while since you've done a trapezoidal one. Remember, we imagined the trapezoid kind of being on its side. And the generic formula, so you have the two bases and the heights. It's the average of the bases times that height, where that height is the distance between those two x values. So again, I made it too easy. We have two trapezoids. One has a width of 2. The other one has a width of 4. The bases are really going to be like the y value. So like if I want to evaluate this integral is going to be, I have base 1 plus base 2, 2 plus negative 4, find the average of those, times the width of that trapezoid, which is 2. And then I'll do it again for the other one, base 1, base 2. Find the average of it times the width of that trapezoid. If this was a quiz or a test, you could leave it like that. I do know we're going to use that integral later on, so I am going to go ahead and evaluate it. So that's going to be what? 2 plus -4, -2 divided by 2 times 2. And then plus, that's going to become -16 divided by 8 times, which is, I'm doing math wrong today, -34. So we can find that number using the Riemann sum, and again, that came from Unit 5. So before we explain it in context, let's see if we can just figure out what the units of that -34 would be. What would be the units of that -34? Meters. Again, pretty easy to think. If we're integrating velocity, then I know that this would be in terms of meters. Is that the exact or the approximate value of that interval? The approximate. We use a Riemann sum. Riemann sums are always approximations. So that's usually the first half of these problems. Like your quiz had a lot of just like set it up and then find the number. There was a few where I had to either like identify it in context or explain it in context. Anyone want to take a stab at what that integral would represent in the context of this problem? If you integrate the velocity from 1 to 7, what would that represent? The displacement. So you can either say this represents the displacement, or you could call that the net distance. Both of those mean the same thing for us in this class. Traveled, or let me put units on there, in meters, which we've already kind of said. Traveled by the particle from t is equal to 1 second to 7 seconds. Key words you would want to make sure your justification have. I did see from the quizzes I have graded, again, I haven't finished, but I did see some like weaker justifications. You would have to mention displacement or net distance. I would tend to call that net distance, but displacement is not wrong. You would have to make sure you're clear about what that would be measured in. It was measured in meters. And then you want to be clear that this is the displacement with a clear starting point and a clear ending point. When did it start? It started at 1 second and ended at 7 seconds. If you just would say something like from t is equal to 1 to 7, that's not clear enough. You don't have units there. If you said like up until 7, that's also not clear because it's not technically up until 7. It's starting at 1 and then ending at 7. Any questions on that row? Yes.
So you couldn't just say t equals 1 to t equals 7.
You would need to put units on there and put seconds, yeah. And the AP exam, just from being a reader last summer, I didn't realize how strict they were about that until I was a reader. And that you have to have units on your time. So yeah.
Did you take off for that yesterday?
I did take off a half a point. We left off the units on the time.
Every time or just once?
Just once. Let's see what time it is. Try numbers 2 and 3 for me on your own. So take a moment, try 2 and 3, and then we'll regroup, go over it, and then see if we have time for 4 and 5. And again, things I'm wanting to kind of emphasize in practicing, like, can you find the number? Yes or no? And then can you describe it in context? Yes or no? Because both of those things are equally important. Me being able to find the number, and then also being able to describe what that number represents in context. Give you a few moments to try that. And again, maybe you can only do the numbers, so you have to wait for us to do the context. Maybe you're good at the context, but not so good at finding the number. I'm going to give you a moment to try just 2 and 3 for now. If you want to go ahead and keep working on all of them, you can. We'll eventually do all of them. I'm kind of chunk it up a little bit at a time. This right here, you just want to make sure you're dividing by 3 pies. 3 pi, like that. air traffic was divided by 3 and then multiplied by 5.
Okay.
And just with how today's gone, more people have had trouble with number 3 versus number 2, which I think is understandable for this problem. So for number 2, it basically looks like number 1, but we're integrating the absolute value of velocity. Well, when you're integrating the absolute value of velocity, it just means make velocity positive. We already saw how in that previous one, how are we finding this integral? We're finding this integral by using a Riemann sum. So basically, I'm just going to use all the positive values. And then that does work out to be 38. What would be the unit of measurement for that numerical value of 38? Meters. So we're still integrating velocity, so it still would be meters. Since we use a Riemann sum, that would be the approximate value of that integral. We don't have enough information to find the exact value. And your description, what that means in context, you really only need to change one part of the description above it. What's the one part you need to change?
Net to total.
Net to total. Several people missed this on the quiz. You forgot that total distance did require the absolute value, but basically this would be the total distance versus the net distance in meters traveled by the particle from, and then being clear, from 1 to 7 seconds. Big idea from that one, that is representing the total distance, not just the net distance. And then number 3, go ahead, Mitchell.
So what I did was I did what happened in number 1,
Mm-hmm.
used that negative 34, and then put the absolute value on that.
So I'm glad you mentioned that because some people did that on the quiz as well. So total distance is described as the integral of the absolute value of velocity. What you did is you just took that 34 and made it positive. So technically what you did, I'm going to kind of go off to the side. You found the absolute value of the integral, which that is not what total distance is. So the total distance, and it has to go on the inside, and the reason is because you're trying to take care of like the backtracking. So like when it moved forward and then maybe backwards. If you have your absolute value on the outside, like you already found the integral, so you ignored the backtracking, you just made it positive. So like making sure when you do total distance, it always needs to go on the inside of that integral. We'll never do something like that top.
Okay.
So then go ahead and look at the third one, and I'll give you some time to try 4 and 5 on your own. I think this one can be kind of tricky. First off, do we know anything about V prime from what was given to us in the problem? No, we just have a table of values of V. Do realize I could have also written this problem as the integral of what function? A of t. Like we know the derivative of velocity is acceleration. Again, still not helpful because we don't know anything about the acceleration. And I think the tricky part of this one is you just need to think back, or really just not overthink it, like what does it mean to integrate a function? Well, this is the integral of v prime. If you're integrating v prime, what function are you going to end up with? V, like the integral of f prime is f, so the integral of v prime is v. And then how do you evaluate a function? You're going to plug in the top number minus the bottom number. So this integral is literally the same thing as v of 7 minus v of 1. And I think that's like a big topic that's often missed because people try to make it more complicated than it is. Or maybe they see the integral and they want to do a Riemann sum so badly. But again, you need to think about like, you don't know v prime, so I can't do a Riemann sum. But I can rewrite it using what I know about the integral and how it works. And then we are, of course, able to find this one, v of 7 and v of 1. We can get that just directly from the table. V of 7 is negative 12, and v of 1 is 2. So I have negative 12 minus 2, which gives me negative 14. The first question I'll ask, what will be the units that is attached to that negative 14? Meters per second, so this is velocity, so it will be meters per second. Would this technically be the exact or approximate value for that original integral? The exact, right? We know exactly how to find the integral. The integral is exactly found by plugging in the top minus the bottom of the antiderivative. That is the exact value. So that's the first part of that problem, just finding that numerical value and the units. What I think also can be tricky about this one is trying to find a way to phrase what that integral represents in the context of this problem. Anyone want to take a guess of a sentence they could use to describe what that integral actually represents? Go ahead.
Net area of the acceleration.
Say it one more time.
Net area of the acceleration.
I'm going to use that same word net. I'm going to use the phrase net change instead. And it's the net change of the velocity. So you can describe it as the net change of velocity, which is measured in meters per second from, again, a time at 1 second to 7 seconds. And where I'm getting net change, I think it's easier to look at like that rewritten version of it and then the integral. Like one, we know in calculus, when we integrate a rate, that does give you a net amount. We're kind of integrating the rate of velocity, acceleration. So the integral of v prime literally means the net change of the velocity from 1 second to 7 seconds, or how much the velocity changed from one starting point to some ending point. Questions on that row? What time is it? All right, guys, it's 3:12, so I'm going to stop there for today. Tomorrow, what we're going to do, in case you're just feeling eager, if you want to go ahead and fill the rest of the table, you can. But basically, my plan is tomorrow is to finish this table, especially the second page, which has a lot of the new formulas, the average rate of change and the average value, both finding the number and finding it in context. What I want you working on to start off with is just that homework number 3. The homework 3 is kind of in 2 parts. The first part is just like find the average value rate of change, like very numerical with the function. The second half is more of the word problems. If you're trying to chunk it, I might just say do problems 1 through 5 tonight, and that would be like, just do that, and that would be good enough. And you'll have time to finish the rest tomorrow. Again, I will be giving a recovery test tomorrow during office hours for that previous unit, so definitely reach out to me if you plan on doing that or need that. Also, I will finish grading the Unit 7 quizzes sometime today. So tomorrow you'll be able to see your grade on that quiz. Also, kind of be on the lookout for, I'm going to post it again on that newsfeed kind of page in Teams, a video of me just explaining each question on the quiz. I think that will be more helpful to a lot of you than just looking at the written version of the answer key. Because again, a lot of this unit is like thinking through the problem, kind of figuring out why we do a lot of things that we do. So that's it for today's notes. If you have questions or things to clarify, definitely